Hi, I'm Emily, a software engineer on Google's Federated Learning team.
Hi, I'm Jake. I'm also a software engineer at Google's Federated Learning team.
And today we'll be talking about federated learning with TensorFlow Federated. So the goal of federated learning is to enable state-of-the-art machine learning without centralizing data and with privacy by default. So here on the screen is a really wordy definition of what federated learning is, but this is really a narrow definition of the model training aspects. Really, federated learning is a practice or approach for solving machine learning problems, which require more than just model training. So let's give some intuition behind why federated learning and other federated computations like federated analytics are exciting. Let's imagine you want a super smart traffic model, but you don't want to send an individual's location information to the server. For smart cars, federated learning could be used to train the traffic model without any of the driver's information leaving the smart car itself, which is pretty cool. Another example here is for hospitals. If you think about hospitals, they contain tons of patient records that are highly sensitive, and hospitals don't really want to centralize this information due to privacy concerns. Federated technologies could enable hospitals to keep this information decentralized and private, and only learn from the information together in aggregate through things like federated analytics and federated learning. Throughout this talk, we'll be detailing mainly cross-device federated learning, which we have a diagram here for. If it's a little confusing, don't worry, we'll be getting into great details of this later on. So this is where a server will be orchestrating federated training, federated evaluation, or other federated computations. And devices will be performing local training or local computation against their own on-device data. The results of that will be aggregated back to the server to produce a new model through federated averaging, etc. This can in turn be deployed to new devices. Another flavor of federated learning, if you've heard of this before, is cross-silo federated learning, which we won't really be focusing on within this talk, but I just wanted to introduce it briefly here. This is federated learning across data silos. It enables organizations, like that hospital use case from before, to collaboratively train a model by aggregating local updates without centralizing any of their data in one place. But again, this won't really be covered much in this presentation. Cool. So today, Jake and I will be talking about why decentralized data is important, why we want to learn from it, what we can learn from it, how to make use of this decentralized data in a secure and private way with things like federated computations, like specifically federated learning, and then how to experiment with these concepts using TensorFlow Federated. Awesome. So let's go ahead and jump in. Why is decentralized data cool and interesting and important? Well, decentralized data is everywhere. There are billions of phones and Internet of Things devices that are constantly generating data. Smartphones themselves, if you kind of think about it, are the world's largest supercomputer. So it's interesting to think of them as collectively decentralized compute nodes. The decentralized data stored on these devices can enable better products and smarter models overall. So if this data starts and lives at the edge, can we actually harness the power of this decentralized data without collecting the data or collecting the data in a centralized location? And why would we want to do this? Well, learning at the edge has many benefits. We see an increase in user experience through things like lower latency to prediction, the ability to use models when the phone itself is offline. Bringing learning to the edge is also better for privacy concerns because the learning is localized to the device itself. This is also better for resource limitations like battery and data caps, since something like a phone wouldn't be transmitting tons of training data or inference requests to a centralized server if you're using on-device learning. So because we only perform on-device training when the device is plugged in and idle, We try to minimize battery usage and performance impact to the device itself. So now that we've seen like all these like benefits of bringing training and learning to the edge, can we actually bring training to the device? And we can with something like federated computation. Passing it off to Jake now.
Yes, now let's switch to federated computation. In short, federated computation is basically a MapReduce for decentralized data with built-in privacy-preserving aggregation method. We'll see what it means in a second. Let's look at a very simple example. Say we have a set of edge devices, which can be a phone or a sensor. On each device, we measure the maximum temperature device saw around the day, and store that information on the device only. Each device keeps their data local, but this comes with some obligations. Now each device is responsible for dataset management locally, with things like expiring old data and ensuring data is encrypted when not in use. Now one engineer wants to answer a specific question of the decentralized data, like what fraction of the users saw a daily high over 70 degrees Fahrenheit. The first step would be for the engineer to input that threshold on the server. Next, the threshold would be broadcast to the subset of available devices the server has chosen to participate in this round of federated computation. Please note in this case, not every device is available for the round of computation, and for all the devices that are available, not all of them are selected. The final selected pool of devices are actually the result of a mutual selection between the server and the clients. Once the threshold is broadcast to the selected pool of devices, this threshold is then compared with the local temperature data to compute the value 0 or 1, depending whether the temperature was greater or lower than the threshold. These values would then be aggregated using the aggregation operator federated min, which encodes the protocol for computing the average value over the participating devices. The server combines reports from multiple devices and only persists the aggregate. Performing the federated aggregation only makes the final aggregated data available to the engineer without giving them any access to individual reports. So what we have just shown is just one round of federated computation. In practice, the server will repeat this process multiple times to get a better estimate of the answer to the engineer's question. As for each round, devices may have dropped out throughout the computation, or some devices may not have been available at the time. Federated computation has challenges that go beyond what we usually experience with distributed computation in the data center. Edge devices like phones tend to have very limited communication bandwidth, even when on a home Wi-Fi. They are also intermittently available, because devices will generally only participate if certain conditions are met, such as idle, charging, and on an unmetered Wi-Fi network. And because each compute nodes keep the copy of their data locally, the data itself is only intermittently available for training. Edge devices, such as smartphones, can also cover a large variety of brand, make, and model, which means there's a lot of heterogeneity in hardware. Finally, any individual update should be ephemeral. Each update should be aggregated with privacy-preserving technologies. Now we'll switch to Emily to talk about federated learning.
Hi, thanks for Jake for covering federated computation. So he just showed you how like federated computation works. But what about the more complex workflows needed to support federated learning? So before jumping into federated learning, let's look at the typical workflow for a model engineer who's performing machine learning in the data center. So typically they'll have some data in the cloud where they'll start training and evaluation jobs. potentially in grids to experiment with different hyperparameters, and they'll monitor how well these different jobs are performing on the data. They'll end up with a model that will be a good fit for the distribution of cloud data that they have available to them. So how does this workflow translate to the federated learning environment? Well, they'll still have some server-side data, but now we refer to this as proxy data, or data that will be similar to what they have available to them on device. This data might be useful for training and evaluating in advance, but now the main training loop will be with the decentralized data on device instead. The model engineer will still do the things that are typical of a machine learning workflow, like starting and stopping tasks, trying out different learning rates or other hyperparameters, and monitoring the performance of their workflow with metrics to determine which model is best. If the model performs well on the decentralized evaluation set, or even on a centralized evaluation set, the model engineer will then have a good release candidate that they can deploy to new devices. Cool, so now that we've seen like a typical workflow, let's jump into how federated learning works. I'll be running through an oversimplification of how FL works, but this should give you the general idea of how it works. So first, if a device is idle and charging, the device will check in with a server and ask the server if it's needed. Most of the time, the server will tell the device to go away and check back in later. It doesn't have any tasks for it to run. But some of the time, the server will have work for the phone to do. So in this case, if a phone has been selected for a round of federated learning, the initial model that's as dictated by the model engineer will be sent to the phone. For an initial model, usually zeros or random initialization is sufficient. Or if they have some of that relevant proxy data in the cloud that we talked about earlier, they might start from a pre-trained model. Other devices will be participating in this round as well, performing their own local rounds of learning. Some of these clients may drop out before uploading their update to the server, but that's okay because the federated learning protocol is resilient to this. The server will aggregate all of the user's updates into a new model by averaging the model updates, optionally using secure aggregation. It's important to note that these updates that each phone sent are ephemeral and discarded after use because they are no longer needed. The engineer will monitor the performance of federated training through metrics that are themselves aggregated along with the model. So training rounds will continue if the engineer is happy with how the model is performing. A different subset of devices will be chosen for each round, and they will be given the newly updated model parameters. So again, it's important to note that federated learning is iterative. This process will continue through many rounds. Cool, so now that we've seen how federated learning works, let's jump in and look at some of the interesting open problems or advances of federated learning within like the machine learning research area. So if you're more interested in the research side of machine learning, researchers on our team have collaborated with many external researchers to collectively produce an advances in open problems and federated learning paper. It's available at that archive link listed here. Let's go ahead and explore this paper now, some of the interesting problems that are open in it. So some interesting areas that federated learning has advanced or some open problems in it is improving the efficiency and effectiveness of this federated environment. So it'd be interesting to expand FL to more ML problem areas or machine learning workflows. So think of like federated learning for semi-supervised learning or unsupervised learning, triplet loss, identity embedding, reinforcement learning, collaborative filtering, and recommender systems. It'd really be cool to make these work in a federated environment. There's also some advancements that could be made in the optimization algorithms that are used for federated learning. There needs to be like an analysis of like how of parallel SGD and local SGD versus like federated averaging, more investigation for convex and non-convex cases. One of the things about the data that's available for federated learning is that it's highly non-IID, so like investigating that further. Federated training can be slower and more expensive than data center training, so how to have less hyperparameter tuning and more like adaptive algorithms. Each model trained has a potential privacy cost, so there's always that. Yeah, cool. Some other open areas are addressing and ensuring fairness and sources of bias within the federated environment. So there's a question of like, how do you even define fairness in the federated learning setting? How can you ensure unbiased and fair models are produced despite the challenges with selection and reporting in the federated environment? Another thing to think about is privacy. Other advances and questions center around this in the federated environment. So to start thinking about this, one step in this direction is to really map out all of the different places that privacy comes up in the federated system. So potential threat models here include compromised devices, a compromised server, data corruption in the network, inference time attacks, etc. We've seen how basic federated learning uses data minimization, focused collection, ephemeral updates, and this only an aggregate principle to minimize what can be learned across the system and address some of these privacy concerns. But federated learning and federated computation also comes with some privacy technologies that are designed to keep a user's information private. So there's things like on-device data sets where each device will keep the raw data local. None of the raw data will be leaving the device itself in federated computation, and the device is responsible for encrypting this data. There's federated aggregation, so the server will combine the reports from all the devices and will only persist the aggregate. Only the aggregate is available to the downstream engineer without giving them access to the individual user's reports. The reports, again, themselves are ephemeral, so they only stay around long enough to be aggregated. There's this concept of secure aggregation, which I'll be getting into in the next slide. The server can only make sense then of the aggregated result, not the individual reports themselves. And then there's differential privacy, which is used to obscure a user's individual impacts on the learned model. So we can only learn information about the group and not the individual themselves. Cool, so let's jump into secure aggregation and see how this works. Secure aggregation allows us to enforce the only an aggregate privacy principle in our technical implementation. Secure aggregation is an optional extension to the client-server protocol that embodies this privacy principle. Here's how it works. So I'm going to walk through a very simplified overview that demonstrates the key idea of how the server can compute a sum without being able to decrypt the individual messages. In practice, secure aggregation is much more complicated, such as like handling phones that have dropped out partway through the protocol. See the paper that's listed in that lower left-hand corner for more details on this. So through coordination by the centralized server, two devices will agree on a pair of large masks that when summed add to 0. Each device will add these masks to their update vectors before reporting. All devices in a round will exchange these pairs if you're doing secure aggregation. And the reports will be completely masked by all of these random values. So you can see how the update itself is being masked. And we can see that the added pairs to each user report look random on their own. But when aggregated together, the pairs cancel out and we're left with only the sum that we're looking for. Again, this was very overly simplified. In practice, the protocol is much more complicated to handle things like dropout. Cool, so now let's introduce another one of the cool privacy technologies associated with federated learning, differential privacy. which is the statistical science of learning common patterns in a data set without memorizing individual examples. So differential privacy ensures that an individual's data is not memorized or learned by the computation. Information is learned about the group and not the individual. So here's an example with differentially private model averaging. This is an example of user-level differential privacy in the federated system. There's also things like example-level differential privacy, which is not represented by this diagram. Devices here, if you're doing it this way, devices will clip their updates if they're too large before sending them to the server. And then the server will add Gaussian noise when combining the updates, which will obfuscate an individual user's information. So here's the basic idea of differential privacy. Awesome. Passing it off to Jake.
So federated learning is an active developing area within Google among the suite of cutting-edge technologies to deliver the best protection of user data. It is used by multiple teams at Google to train and evaluate powerful machine learning models on decentralized data. It has been used to power features on Pixel devices and used in apps such as Gboard and Android Messages. The app powered by the federated learning technology has more than 500 million installs. More and more teams within Google is adopting this new technology. Let's first look at some real use case inside the Gboard app. The first example we are looking at is next word prediction, where we want to predict the next word based on the user typed text so far. The machine learning models used to achieve this powers the prediction strip inside the Gboard app. This is a very nice example of a typical federated learning task. The data is privacy sensitive. Training on data with real user interaction is critical to the success. And the feedback signal, or say the labels for the data, is naturally available on device. By using federated learning technology, a federated RNN model was successfully trained and replaced the prior N-gram model. As a result, we observe a 24% improvement in accuracy, which has a big impact on users' experience with the keyboard, and also resulting 10% more clicks on the prediction strip. Since this launch, the Gboard app has deployed federated learning for a variety of models and applications in the keyboard, including predicting relevant emoji suggestions or actions like stickers and GIFs, and doing analytics to discover new words. So we have looked at some success stories on how to use federated learning to train a machine learning model. Now let's look at an example of use federated technology to do diagnostic and analytics in a privacy-preserving way. Federated analytics is used to support now playing feature on Google's Pixel phones. It is a tool shows you what song is playing in the room around you. Under the hood, now playing uses on-device database of song fingerprints to identify music playing near the phone without the need for a network connection. To measure and improve each regional database quality, the engineers needed to answer a basic question. Which of the songs are the most often recognized? Federated analytics provides an answer without revealing which songs are heard by any individual phone. It is enabled for users who agreed to send the device-related usage and diagnostic information to Google. So after I told you so many success stories about federated learning, you may wonder, how can I try it myself? Now, let me introduce the TensorFlow Federated, TFF. It is a community project for everyone to develop the building blocks of federated computations and run simulations. TensorFlow Federated, TFF, is an open source framework for producing federated computations using decentralized data. It powers both federated learning and federated analytics. TFF is actively used by Google in our own federated learning production system and federated research both internally and externally. It is also an open source project within the TensorFlow ecosystem. The ultimate goal of TFF is to make your computation easily portable so that you can write your federated computation code only once, but deployed anywhere, such as local simulation with single or multiple machines, used for cross-silo deployment, or maybe deploy your model on mobile IoT devices. Currently, only simulation is supported inside TFF. Our team is actively working on expanding the capability of TFF, and of course, external contribution from you guys are welcome, especially for different runtime like on-device development. There are three major parts inside the TFF toolbox. First, there's a high-level API, TFF.learning, which contains the implementation of common FL algorithms, such as the federated averaging, and emerging research code based on TFF. It is best suited for engineers and researchers to just try the federated learning technology out of the box with your existing model. For researchers who are interested in building their own federated learning algorithms, the Federated Core API is a better fit. The Federated Core API, FC API, contains abstraction and execution models for the federated computation. It is the building foundation of everything else within TFF. TFF also offers other components to facilitate with the simulation needs, including the datasets and the simulation runtime with single or multiple machines, CPU or GPU support, and also GCP and Kubernetes support. First, let's dive into high-level API, the TFF.learning. TFF.learning API comes with convenient methods for building a federated training computation or federated evaluation computation with the existing TF model. If you know Keras already, you can directly plug in the existing Keras model with just one line of code. You can easily build a federated computation. Once you constructed the train and eval computations, here's the few lines of code to run the federated training and evaluation in simulation. In this example, we are running 5 rounds of federated training. We can evaluate the produced model by using our federated evaluation computation, passing in the produced model and the trained data. So by default, a single machine in-process runtime is spawned in the background. If you are interested in running simulation in multi-machine environment, please follow the link on this page to our tutorials about how to use Kubernetes for high-performance multi-machine simulation. When the FL API is not enough for your needs, you probably can check out the lower level core API for more advanced custom applications. The federated learning API itself is also built on top of the FC API. Before I dive into details of the federated core API, I would like to introduce the concept federated value. A federated value is a value which can exist on the client or on the server. This comes with both a type and a placement. Thinking about the example I mentioned in the slides before, the temperature reading on the edge devices can be expressed as a federated float 32 values with placement at the client. A federated computation is a computation with federated values as input and output. Federated computation runs in the network, not just on the device, nor just on the server. You can consider federated computation lives between the two. A federated computation is composed of federated operators. You can think of a federated operator as a function whose input and outputs can live both at the client and the server. This involves orchestration and communication between the clients and the server in a controlled way. And the communication is an essential part of the program logic. Each client's reports are only used in aggregate back on the server. So let's go back to our example I showed earlier in the slides, and to illustrate what this looks like with the TFF code. As a reminder, we have an engineer who would like to know the fraction of temperature sensors with readings of a specific threshold. The reading of the temperature are federated values at the client, and the threshold is a federated value at the server. There are 3 federated operators involved in this example: the federated broadcast, federated map, and federated min. I will go into details about what these operators do in a second. These operators represent the communication between the clients and the server. This example creates a federated computation denoted by a special function decorator, TFF the federated computation. A federated computation can have both client-side input, in this case is the temperature reading on each device, and the server-side input, which is the threshold of the engineer would like to compare to the on-device data. Federated computations have federated operators whose input and outputs live in different locations. Could be both at server and at clients. In this example, we use TFF the federated broadcast to transfer the threshold value from the server to the client, and use the federated map operator, which is like the map step in the map reduce, used to tell the clients to compare their data against the threshold, producing a value of 1 if the temperature is over the threshold, or 0 if the temperature is below the threshold. And finally, a federated mean to get the result back at the server of the fraction of devices with temperature readings that are over the threshold. Each client receives a TensorFlow code to execute locally. In this case, a TF function called exceeds threshold function is sent to the client to compare its temperature reading with the received threshold. This particular function is just used for on-device processing. It is important to note that although the TFF code is expressed in Python, it's actually not a Python. The invoked federated computation is not implemented in Python because the ultimate goal of TFF is to deploy federated computation on edge devices, where usually Python is not available. At the definition time, the code annotated with TFF the federated computation decorator will be traced and serialized for later use. This mechanism is very similar to how the TensorFlow graph mode works. If you take a closer look at the computation protobuf message, this is how we serialize the computation. You can see that TFF computation can have several kinds of different forms, including the TensorFlow ops, or a federated operator, or maybe a lambda calculus. I know this is a very fast and brief introduction of how to coding with TFF. If you want to see more information, please visit our page at tensorflow.org/federated to get more detailed documentation. We also hosted a federated learning workshop in the summer. This year in the workshop, we included a much more in-depth tutorial of TFF. If you are interested, please follow the link on the slides to watch the recording on the YouTube. We also love external collaborations and contributions from you guys. Feel free to contribute to TFF using GitHub. If you want to have another look at the idea we introduced today, or you simply love quirkies, please check out the Federated Learning Comic Book at federated.withgoogle.com. We were very fortunate to work with 2 incredibly talented comic book artists to illustrate this very complex concept as a graphic art. Thanks for listening.